There's something about the cosmos that refuses to let us look away. Every time we think we've unraveled its secrets, the universe throws another curveball our way, something so bizarre, so inexplicable, it leaves even the brightest minds scratching their heads. Take a moment to picture this: trillions of stars, galaxies stretching farther than we can fathom, and hidden among them, mysteries that defy logic. These aren't just gaps in our knowledge, they're cosmic riddles whispering that we've barely begun to understand the true nature of reality. That's what makes space anomalies so thrilling. Unlike the predictable orbits of planets or the steady glow of distant suns, these are the outliers, the phenomena that shouldn't exist, yet there they are, staring back at us through telescopes and data feeds. Some pulse with energy we can't explain. Others vanish without a trace. A few seem to break the very laws of physics as we know them, and the most fascinating part: no matter how many theories we throw at them, these enigmas refuse to be solved. They're the universe's way of keeping us humble, reminding us that for all our advancements, we're still just beginning to explore. Today, we're diving into 25 of the most jaw-dropping space anomalies ever recorded. From celestial objects that shouldn't exist to signals from the void that hint at something beyond our comprehension, each one is a story of confusion, wonder, and the relentless curiosity that drives us to keep searching. These aren't just scientific puzzles, they're invitations to imagine, to question, and to marvel at how much we still don't know. So buckle up. By the time we're done, you'll see the night sky a little differently, knowing that behind its serene beauty lies a universe teeming with mysteries waiting to be uncovered. Imagine a quiet summer night in 1977, the stars shining down as usual, when suddenly, a burst of radio waves tears through the cosmos, so powerful and precise that it stops astronomers in their tracks. For 72 seconds, the Big Ear telescope at Ohio State University locked onto something extraordinary, a signal unlike anything ever detected before or since. It was so remarkable that when researcher Jerry Amon saw the data printout, he circled the reading in red ink and wrote one word beside it: "Wow." And just like that, the wow signal became one of the most tantalizing mysteries in the history of astronomy. What made this signal so special? First, its intensity 30 times stronger than the background noise of space. Then, its frequency, 1420 MHz, a range scientists had pinpointed as ideal for interstellar communication because it's naturally quiet, with minimal interference from cosmic phenomena. But perhaps the most puzzling detail, it vanished as abruptly as it appeared, never repeating despite decades of searches in the same patch of sky. Experts have spent years debating where it came from. Some argue it could have been a natural event, a comet's hydrogen emission or a passing satellite's reflection. Others point out that its narrow frequency band and steady drift match what we might expect from an alien transmitter. Then there's the unsettling truth: we may never know for sure. The wow signal's fleeting nature left too little data to confirm a source, turning it into a cosmic riddle that lingers like a whisper just beyond our reach. Beyond the science, the wow signal captured imaginations worldwide, fueling debates about extraterrestrial life and even inspiring music, films, and conspiracy theories. It's a reminder that sometimes the universe doesn't give us answers, it gives us questions that push us to look deeper, listen harder, and wonder what else might be out there waiting to surprise us. The universe is incomprehensibly vast, with hundreds of billions of galaxies, each containing trillions of stars, many orbited by planets in the so-called habitable zone. Statistically, life beyond Earth seems almost inevitable. And yet, when we scan the skies for signs of intelligence, radio signals, megastructures, anything, we find only silence. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a question that haunts astronomers and philosophers alike, because if life is so likely, why does the cosmos seem so empty? One terrifying possibility is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. It could be behind us, meaning the evolution of intelligent life is far rarer than we think. Or worse, it could lie ahead, an existential threat like self-destruction through war or environmental collapse that wipes out civilizations before they can spread. Either way, the silence might be a warning. Then there's the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact, observing us like animals in a cosmic wildlife reserve. Or perhaps interstellar travel is impossibly difficult, with physics or energy constraints locking civilizations to their home systems. Some suggest we're simply too early, that the universe is young, and we're among the first to ask these questions. The chilling reality is that we don't know. The Fermi Paradox forces us to confront how little we understand about life's place in the universe. Are we alone? Are we pioneers, or are we missing something fundamental? Until we find answers, this paradox remains one of space's deepest, most unsettling mysteries, a quiet void that speaks volumes about our search for meaning among the stars. The universe holds its secrets close, and none are more frustrating or more pervasive than dark matter. Picture this: every star, planet, and galaxy we see makes up less than 5% of the cosmos. The rest, a staggering 27%, is this invisible, ghostly substance that refuses to interact with light, yet its gravitational pull shapes the very fabric of space. Without it, galaxies would fly apart, their stars scattering into the void like marbles flung from a broken string. Scientists first stumbled onto dark matter's existence in the 1930s, when astronomer Fritz Zwicky noticed something bizarre about galaxy clusters. They moved too fast, so fast that the visible mass holding them together should have been ripped apart. Something unseen was acting as cosmic glue, and though we still can't see it, we feel its presence everywhere. Take the famous Bullet Cluster. Two galaxies collided, their visible gas slowing down like cars in a traffic jam, while their dark matter sailed straight through, dragging stars behind it like an invisible hand. The hunt to identify dark matter has become one of science's greatest detective stories. Deep underground, in mines shielded from cosmic noise, detectors wait for the faintest tremor, a sign that a dark matter particle has finally bumped into ordinary matter. Meanwhile, the Large Hadron Collider smashes protons together at nearly light speed, hoping to create these elusive particles in the debris. Some theories suggest they could be WIMP, weakly interacting massive particles, so heavy and slow-moving they pass through us unnoticed. Others propose actions, particles so light they behave more like waves. Yet after decades of searching, dark matter remains a shadow. It doesn't absorb, emit, or reflect light, and it refuses to interact with the forces that bind our familiar world. Some researchers even question whether we've been chasing a phantom. Could gravity itself work differently on cosmic scales? But the evidence piles up. The bending of light around galaxy clusters, the cosmic microwave background's faint fingerprints, even the way galaxies spin faster than they should. The implications are staggering. If we ever capture dark matter, it could rewrite the laws of physics, revealing hidden dimensions or new forces of nature. Until then, it stands as a humbling reminder. Most of the universe is made of stuff we can't see, touch, or even fully comprehend, a mystery woven into the darkness between the stars. If dark matter is the universe's invisible scaffolding, dark energy is its phantom engine, an enigmatic force pushing everything apart at an ever-increasing speed. Imagine blowing up a balloon with galaxies painted on its surface, then watching in awe as the balloon inflates faster and faster, not because of your breath, but because of some unseen hand tugging at the fabric of space itself. That's dark energy in action, making up a staggering 68% of the cosmos and defying everything we thought we knew about gravity. Unlike dark matter, which binds galaxies together with its gravitational pull, dark energy does the opposite. It stretches the universe apart, driving an expansion so relentless that distant galaxies are now receding faster than light. The discovery of this phenomenon in the late 1990s shocked astronomers studying distant supernovae. They expected the universe's expansion to slow down over time, pulled back by gravity's grip. Instead, they found it was accelerating, as if space itself had a hidden repulsive force. Theories about dark energy's nature range from the mind-bending to the deeply unsettling. One leading idea is vacuum energy, a sort of cosmic background hum where empty space isn't truly empty but seethes with particles flickering in and out of existence. According to quantum physics, these fleeting fluctuations could generate a pressure that pushes the universe outward. But here's the catch. Calculations suggest this energy should be unimaginably stronger than what we observe, leaving scientists puzzled by the discrepancy. Then there's quintessence, a hypothetical field permeating space that changes over time, unlike the constant push of vacuum energy. Picture it as an invisible fluid, thinning or thickening as the universe evolves, its properties shifting in ways we can't yet predict. Some models even suggest dark energy might one day rip the universe apart in a catastrophic big rip, tearing galaxies, stars, and even atoms asunder in a far future apocalypse. The most unsettling part, dark energy might not be a single force but a symptom of something deeper, a sign that Einstein's theory of gravity, while brilliant, is incomplete on cosmic scales. Alternative theories propose that gravity itself behaves differently across vast distances, eliminating the need for dark energy altogether. Yet every time we test these ideas, the evidence for dark energy's reality only grows stronger, from the cosmic microwave background's subtle patterns to the large-scale structure of galaxy clusters. What makes dark energy so humbling is how little we grasp its origins or destiny. It dominates the universe's budget, yet we can't detect it directly, only infer its presence by the way galaxies flee from one another. Whether it's an inherent property of space, a dynamic field, or a clue to entirely new physics, one thing is clear. Dark energy is rewriting the story of the cosmos, and we're just beginning to decipher its strange, silent script. Some stars flicker like distant candles in the cosmic breeze, but then there's Tabby's star, a celestial oddity that behaves more like a malfunctioning light bulb. Officially catalogued as KIC 8462852, this unassuming star in the constellation Cygnus has baffled astronomers since 2015, when volunteers with the Planet Hunters project noticed something impossible. Its light would plunge by up to 22% at irregular intervals, dimming in ways no natural phenomenon could explain. Stars typically dim when planets pass in front of them, but those dips are predictable, shallow, and brief, nothing like the chaotic, jagged shadows cast by Tabby's star. Theories erupted like wildfire. Could it be a swarm of comets, a colossal impacts debris? The data didn't fit. Comets would leave telltale infrared heat signatures, and dust clouds would scatter light in specific ways. Neither matched what telescopes observed. That's when the wildest hypothesis took hold: alien megastructures, specifically a Dyson sphere, a hypothetical energy-harvesting shell built by an advanced civilization around their star. The idea, first proposed by physicist Freeman Dyson in the 1960s, suddenly didn't seem so far-fetched. Here was a star dimming as though something enormous and artificial was partially blocking its light, a cosmic construction project on a scale we could barely imagine. Subsequent studies poured cold water on the extraterrestrial excitement, sort of. In 2017, NASA Kepler and Spitzer telescopes revealed the dimming was wavelength dependent, meaning certain colors of light were blocked more than others. That pointed to fine dust particles, not solid megastructures, yet the mystery deepened. Dust should be blown away by stellar radiation unless constantly replenished, and nothing in our astrophysical playbook explains how. Even stranger, historical data showed Tabby's star had faded by 14% between 1890 and 1990, a century-long dimming no known stellar behavior accounts for. Today, the star remains an enigma, flickering unpredictably like a cosmic Morse code we can't decipher. Some researchers propose a shattered planet's debris creating uneven dust rings. Others speculate about rogue black holes or interstellar objects warping our view. But with each new observation, the puzzle only grows more complex, defying easy categorization as either natural or, dare we say it, something else entirely. Tabby's star is a reminder that the universe doesn't owe us tidy answers, and sometimes the most tantalizing mysteries are the ones that refuse to fit into any box we try to build for them. On October 19, 2017, astronomers in Hawaii spotted something extraordinary, a visitor from beyond our solar system, tumbling through space at nearly 200,000 miles per hour. They named it Oumuamua, Hawaiian for scout or messenger from afar, and it was unlike anything we'd ever seen. Most asteroids and comets follow predictable orbits, but Oumuamua's trajectory was a hyperbola, meaning it wasn't bound by the sun's gravity. It had come from another star system, making it the first confirmed interstellar object ever detected. But Oumuamua's strangeness didn't stop there. As telescopes tracked its path, researchers noticed something bizarre. It was accelerating as if pushed by an unseen force. Comets often speed up when sunlight vaporizes their icy surfaces, creating a gaseous tail that acts like a thruster. Yet Oumuamua showed no visible tail, no coma of gas and dust, just a silent, unexplained boost in speed. Then came the real shock, its shape. Based on changes in brightness, scientists deduced it was elongated, perhaps 10 times as long as it was wide, spinning like a cosmic cigar. Nothing in our solar system matches that profile. The scientific community scrambled for explanations. Could it be a rare type of comet with hidden outgassing? Perhaps an exo-Pluto, a fragment from a distant dwarf planet stripped of volatiles by eons in interstellar space. Each theory had holes. If it was a comet, why no debris trail? If a rocky asteroid, what caused the acceleration? Then came Harvard astrophysicist Avi Loeb's provocative suggestion. Maybe Oumuamua wasn't natural at all. Loeb proposed it could be artificial, a light sail, a fragment of alien technology drifting through the cosmos. His argument hinged on the object's unusual reflectivity and its unexplained push, which he likened to the way sunlight propels human-made solar sails. The backlash was swift. Critics accused Loeb of sensationalism, pointing out that extraordinary claims require extraordinary evidence. Yet Loeb countered, shouldn't science at least consider the possibility? After all, Oumuamua's properties fit no known category perfectly, and its arrival alone was statistically unlikely. The debate rages on. Subsequent studies suggested Oumuamua might have been a nitrogen iceberg, sheared from a Pluto-like exoplanet, or a cosmic dust bunny formed in a distant stellar nursery. But with the object now beyond our telescope's reach, we may never know for sure. Oumuamua remains a tantalizing enigma, a silent messenger that challenged our assumptions, forcing us to ask, in a universe so vast, how many more oddities are sailing unseen through the dark? One moment, the cosmos is quiet, then, in less time than it takes to blink, a burst of radio waves erupts with the energy of 500 million suns. These are fast radio bursts, or FRB, some of the most baffling signals ever detected in the universe. Lasting mere milliseconds, they arrive without warning, often from galaxies billions of light-years away, and then vanish just as suddenly, leaving astronomers scrambling for answers. What makes FRB so intriguing is their sheer power and unpredictability. The first was discovered in 2007, buried in radio telescope data from 2001, like a cosmic message left unread for years. Since then, we've detected hundreds more, with a rare few repeating at irregular intervals. The most famous repeater, FRB 121102, has flared up dozens of times since 2016, sometimes in frantic clusters, other times falling silent for months. This behavior defies most natural explanations. Celestial events like supernova or neutron star collisions are one-offs, not encores. So what could possibly generate such intense, fleeting signals? Magnetar's highly magnetized neutron stars are a leading suspect. In 2020, astronomers caught one in our own galaxy emitting an FRB-like pulse, bolstering the theory that these cosmic powerhouses could be responsible. Imagine a star so dense that a teaspoon of its material would weigh 1 billion tons, wrapped in a magnetic field trillions of times stronger than Earth. When these fields twist and snap, they could unleash bursts of energy detectable across the universe. But magnetars might not explain everything. Some FRBs are so energetic that even these extreme objects strain to account for them. Could colliding black holes or evaporating primordial black holes be the culprit? Or something more exotic like cosmic strings, hypothetical defects in spacetime left over from the Big Bang? Then there's the provocative, albeit unlikely, idea of artificial origins. Could FRBs be alien beacons, propulsion systems, or even the byproduct of interstellar engineering? The repeating patterns have fueled speculation, though most scientists lean toward natural explanations, given the burst's vast distances and the energy required. The mystery deepens when we consider how FRBs travel. As these signals race through space, they interact with the sparse matter between galaxies, slowing slightly in a way that reveals the universe's hidden structure. This dispersion measure acts like a cosmic odometer, telling us how far they've come. Yet some FRBs arrive with bizarre properties, like one in 2020 that seemed to smear in a way never seen before, hinting at extreme environments near their sources, perhaps near a supermassive black hole or in a turbulent galactic core. Every new detection adds another piece to the puzzle, but the full picture remains frustratingly out of reach. With projects like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, now scanning the skies around the clock, we're uncovering more FRBs than ever, each one a fleeting whisper from the distant universe. Whether they're the cries of dying stars, the echoes of cosmic collisions, or something even stranger, these bursts remind us that the universe is far from silent. It's crackling with mysteries, waiting for us to listen. Galaxies might seem eternal from our vantage point, but in reality, they're cosmic predators, locked in a slow-motion battle for survival. Take Andromeda, our closest galactic neighbor, a stunning spiral that's actually a voracious cannibal, shredding smaller galaxies and absorbing their stars into its own swirling mass. This process, known as galactic cannibalism, isn't science fiction. It's written across the night sky in faint, ghostly trails called stellar streams. These are the remnants of dwarf galaxies torn apart by Andromeda's gravity, stretched into shimmering ribbons of stars that orbit like cosmic tinsel. One of the most famous, the giant stellar stream, wraps around Andromeda like a scar, a silent testament to a meal consumed billions of years ago. But Andromeda isn't the only galaxy with a dark appetite. Our own Milky Way is guilty of the same cosmic feasting. The Sagittarius dwarf galaxy, once a separate entity, is now being pulled apart by our galaxy's gravity, its stars scattered into a looping stream that encircles us. Then there's the Gaia sausage, the shattered remains of a galaxy that collided with the Milky Way 8 to 10 billion years ago. A collision so violent it warped our galaxy's shape and left behind a sausage-shaped cluster of stars hurtling through the halo. These mergers aren't just destructive, they're creative forces, seeding galaxies with fresh stars and altering their structures in ways we're only beginning to understand. And here's the twist: the Milky Way and Andromeda are on a collision course themselves. In about 4.5 billion years, the two galaxies will begin a gravitational dance, spiraling toward each other until they merge into a single, colossal galaxy, dubbed Milkdromeda. Simulations show their mutual pull will warp their shapes, flinging stars into new orbits like marbles in a hurricane. Yet, despite the cosmic spectacle, individual stars are unlikely to collide. Space is so vast that even in a galactic merger, most will pass like ships in the night. This raises a profound question. If galaxies grow by consuming each other, what does that mean for their evolution? The standard model suggests large galaxies form hierarchically, gluing together smaller ones over time. But the details are messy. Some mergers trigger frenzies of star formation, while others leave galaxies red and dead, their gas stripped away, their stellar nurseries shut down. Andromeda, for instance, shows signs of both violent mergers in its past, yet surprisingly little recent star birth. Is this because it's exhausted its snack supply, or are there other forces at play? The answers could reshape our understanding of cosmic history. Stellar streams act as fossil records, revealing not just what galaxies ate, but when and how. By studying their chemistry and motion, astronomers can reconstruct ancient collisions, piecing together the Milky Way's growth like detectives solving a billion-year-old crime. And with next-generation telescopes like the Vera Rubin Observatory poised to map millions more streams, we're on the verge of uncovering the full story of galactic cannibalism, one that's written in starlight, hidden in plain sight. So the next time you gaze at Andromeda, remember, it's not just a pretty spiral. It's a predator, a survivor, and eventually our galaxy's fate. And in that merger, as in all cosmic feasts, lies a deeper truth. The universe doesn't just build. It consumes, transforms, and remakes itself, one collision at a time. Somewhere beyond the familiar sprawl of galaxies, hidden behind the Milky Way's blinding starlight, lies a force so powerful it's tugging entire clusters of galaxies toward it like a cosmic siren. This is the Great Attractor, a gravitational anomaly centered roughly 220 million light-years away in the direction of the constellation Centaurus. Imagine the universe as a rushing river, and every galaxy within 500 million light-years caught in its current, drifting toward a point we can't even see clearly. The scale is staggering, thousands of galaxies, including our own, moving at over 600 miles per second toward something invisible. The mystery deepens when we try to look directly at it. The Great Attractor lies in what astronomers call the zone of avoidance, an area obscured by the dense gas, dust, and stars of our galaxy's disk. It's like trying to spot a lighthouse through a blizzard. The Milky Way's brilliance drowns out the faint light from beyond. Early attempts to study the region were like mapping a shadow, relying on radio and infrared telescopes to pierce the veil. What they revealed was unsettling. An immense concentration of mass, perhaps a supercluster of galaxies far denser than expected, lurking in the darkness. But even that might not explain the full pull. The Norma cluster, a massive gathering of galaxies near the Great Attractor's suspected core, is impressive, but calculations suggest it's not nearly heavy enough to account for the motion we observe. This has led to wilder theories. Could there be a gargantuan, unseen structure beyond it? Some propose the Vela supercluster, a sprawling web of galaxies only recently confirmed as part of the answer. Others wonder if dark matter is clumped in strange, unprecedented ways, warping spacetime more intensely than our models predict. The real enigma is what this means for our place in the cosmos. The Great Attractor isn't the end of the journey, it's just one stop on a far grander voyage. Beyond it lies the Shapley supercluster, an even more massive collection of galaxies pulling us toward itself. This cosmic tug-of-war hints at structures so vast they redefine our understanding of the universe's architecture. What we're seeing might not be a single attractor at all, but a chain of hidden giants, each tugging the next in a dance stretching across hundreds of millions of light-years. For now, the Great Attractor remains half hidden, its secrets shielded by the very galaxy we call home. But with every new telescope and deeper survey, we peel back another layer of the obscuring dust, inching closer to understanding the force that's silently guiding our motion through the cosmos. It's a reminder that sometimes the universe's most profound mysteries aren't just out there, they're hidden in plain sight, waiting for us to look in the right way. In the vast tapestry of the cosmos, where galaxies cluster like cities in the night, there's a place so empty it defies comprehension, the Boötes Void. Picture a sphere of space 330 million light-years across, a region so barren that if you stood at its center, you'd see almost nothing in any direction. No glittering galaxies, no swirling nebulae, just an overwhelming, almost unsettling void. Astronomers call it the Great Nothing, and it's one of the largest known structures in the universe by virtue of being a structure of nothing at all. The story of the Boötes Void begins in 1981, when astronomer Robert Kirshner and his team stumbled upon it while mapping galaxy distributions. What they found was staggering: a cosmic desert where fewer than 60 galaxies reside, a number that should be in the thousands. To put that in perspective, a typical region of space that size would contain at least 10,000 galaxies. The void isn't just sparse, it's a glaring anomaly, a hole punched in the universe's otherwise crowded fabric. But how could such a void exist? One theory suggests it's the aftermath of a cosmic collision, not between galaxies, but between entire universes. In the speculative bubble universe model, our universe might have bumped into another during its early expansion, leaving behind a scar of emptiness. Others propose it's the imprint of an ancient supervoid, where dark energy pushed matter apart so aggressively that galaxies never formed. Then there's the statistical fluke argument. Maybe, against all odds, randomness simply left this patch of space empty, like a single blank tile in an otherwise mosaic-covered wall. The eerie thing about the Boötes Void isn't just its emptiness, it's the contrast. Surrounding it are some of the universe's densest galaxy clusters, making the void's borders almost unnaturally sharp, as if drawn by an invisible hand. Some researchers even speculate that its existence challenges the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions. If the void isn't a fluke, it could mean our understanding of large-scale cosmic structure is missing something fundamental. Yet the void isn't entirely lifeless. The few galaxies it does contain are oddities themselves, isolated, aging, and strangely quiet, as if the void has sapped their vitality. One of them, a dim spiral named MCG +0102, sits alone like a lone tree in a wasteland, its stars burning faintly against the oppressive dark. Studying these galaxies offers clues. Their peculiar motions suggest the void might be filled with dark matter, its gravitational pull too weak to form new stars but strong enough to shape what little remains. The Boötes Void forces us to confront how little we know about the universe's architecture. Is it a rare accident, a cosmic blind spot, or is it evidence of forces or phenomena we've yet to imagine? For now, it stands as a silent enigma, a reminder that even in a universe teeming with light and life, there are places where the rules, if there are any, remain written in shadows. When a star dies in a supernova explosion, the blast is so violent it should obliterate everything nearby, yet somehow, planets still orbit in the aftermath. The first confirmed worlds beyond our solar system weren't found around a sun-like star, but around a cosmic zombie, pulsar B 1257+12, a pulsar spinning furiously in the constellation Virgo. Discovered in 1992, these planets defied every expectation. Pulsars are the corpses of massive stars, their cores crushed into city-sized spheres of pure neutronium, spinning hundreds of times per second and blasting deadly radiation into space. The idea that any planet could survive their birth is like finding a sapling still standing after a nuclear blast. The story of pulsar planets begins with their impossible survival. When a massive star goes supernova, the outer layers explode outward at millions of miles per hour, while the core collapses into a neutron star. For planets to persist, they'd either have to withstand this apocalyptic force, unlikely, or form from the debris afterward, a process no one thought possible in such a hostile environment. Yet there they were, 3 rocky worlds orbiting pulsar B 1257+12, their existence betrayed by slight wobbles in the pulsar's hyper-precise radio pulses. 2 were Earth-sized, 1 Moon-sized, all bathed in lethal X-rays and gravitational forces that could shred a planet's surface. Even stranger is how these worlds might have formed. One theory suggests they're the scorched remains of a gas giant, its outer layers vaporized by the supernova, leaving behind a skeleton of rock and metal. Another proposes a second chance at creation. The explosion's debris might have coalesced into a disk around the pulsar, much like the disks around young stars where planets normally form. Imagine a cosmic phoenix, a new planetary system rising from the ashes of its predecessor, forged in conditions so extreme they rewrite the rules of what's possible. Then there's the question of life. Pulsar planets exist in a perpetual hellscape. Their surfaces, if they have any, would be scoured by radiation and tidal forces, their skies lit by a pulsar strobe-like beams instead of sunlight. Yet some scientists speculate that beneath miles of ice or rock, protected from the worst of the radiation, subterranean oceans might persist, warmed by tidal friction or radioactive decay. It's a long shot, but if life could emerge near volcanic vents in Earth's oceans, why not here? The discovery of pulsar planets forced astronomers to expand their definition of a habitable zone. No longer just the Goldilocks region where liquid water can exist, it now includes any environment, no matter how brutal, where energy and chemistry might conspire to create life. And with each new pulsar system found, like the diamond planet pulsar J1719-1438, a world possibly made of crystallized carbon, we're reminded that the universe's creativity far outstrips our own. These aren't just oddities, they're proof that planets can thrive where we least expect them, turning stellar graveyards into cradles for new worlds. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, it's like seeing the universe's baby photo, a near-uniform sea of radiation with tiny temperature fluctuations that reveal the seeds of galaxies and galaxy clusters. But one of these fluctuations stands out like a bruise on an otherwise smooth surface. Known as the CMB cold spot, this region is colder than its surroundings by about 70 microkelvin, a small difference but statistically significant enough to raise eyebrows. Stretching nearly 1.8 billion light-years across, it's a cosmic oddity that refuses to fit neatly into our models of the early universe. The simplest explanation points to a supervoid, an enormous, underdense region of space where matter is unusually sparse. Supervoids are known to slightly cool the CMB due to the Sachs-Wolf effect. Photons passing through them lose energy as they climb out of the void's weakened gravitational well, shifting the light to longer, colder wavelengths. But here's the problem: the cold spot is too cold. Even the largest known supervoids can't account for the temperature drop we observe. Some researchers suggest it might be a chance alignment of smaller voids, amplifying the effect, but simulations show the odds of such a perfect coincidence are astronomically low. This mismatch has led to wilder possibilities, like the idea that the cold spot is a collision scar from another universe. The multiverse hypothesis suggests our cosmos is just one bubble in an infinite froth of universes, each with its own physical laws. If a neighboring bubble brushed against ours during inflation, the jolt could have left behind an imprint, a cold, underdense region where the energy of the collision drained away. It's a speculative idea, but one with tantalizing implications. If true, the cold spot could be our first glimpse beyond the boundaries of our own universe, a cosmic handshake from an alien reality we may never fully comprehend. Yet skeptics argue the multiverse explanation is a last resort. They point to alternative physics, like exotic dark energy behavior or primordial magnetic fields, that might mimic the cold spot's signature without invoking parallel universes. Others propose it's an illusion caused by foreground structures distorting our view, like a smudge on a camera lens. The debate hinges on a deeper question: when do we accept that an anomaly is truly anomalous rather than a fluke or a gap in our understanding? The cold spot tests the limits of Occam's razor, forcing us to weigh simplicity against the thrilling possibility that we're seeing something entirely new. For now, the cold spot remains an open case, a cosmic whodunit written in microwaves. Whether it's a void, a multiverse calling card, or something stranger, its existence reminds us that the universe's oldest light still holds surprises. And as telescopes like the Euclid satellite map the large-scale structure of the cosmos in unprecedented detail, we might finally get our answer, or find the mystery only deepens. Most galaxies fit into familiar categories: spirals with their sweeping arms, ellipticals like cosmic blobs, or irregulars with their chaotic shapes. Then there's Hoag's Object, a galaxy so bizarre it looks like it was painted by a celestial artist with a compulsive love of perfect circles. Discovered in 1950 by astronomer Arthur Hoag, this ring galaxy floats in the constellation Serpens like a cosmic bullseye, its golden core surrounded by an almost impossibly symmetrical blue ring of young, hot stars. What makes it truly strange isn't just its beauty, it's the sheer emptiness between these two components. Unlike most ring galaxies, where faint bridges of dust or stars connect the core to the outer ring, Hoag's Object offers no such link. It's as if someone took a conventional galaxy, removed everything but the nucleus and outermost edges, and left the middle startlingly blank. Theories about how this cosmic oddity formed read like a list of astronomical what-ifs. One leading idea involves a galactic collision, a smaller galaxy piercing the disk of a larger 1 billion of years ago, sending shockwaves through its gas and triggering a wave of star formation that rippled outward into a ring. This process, known as a density wave, is similar to how spiral arms form, except here it would have created a near-perfect circle. But there's a catch: no visible remnant of the intruder galaxy exists, and simulations struggle to explain why the ring would remain so symmetrical over eons without dispersing or warping. Another hypothesis suggests Hoag's Object is a rare case of extreme resonance. Just as Saturn's rings are shaped by the gravitational tug of its moons, the galaxy's central bar, if it ever had, one might have orchestrated the outer ring's structure through rhythmic gravitational pulls. Yet Hubble telescope images show no sign of a bar, leaving this theory on shaky ground. Then there's the possibility of accretion, where the galaxy siphoned gas from intergalactic space, funneling it into a ring where new stars ignited. But without traces of incoming material, this too feels incomplete. The real enigma lies in what Hoag's Object implies about galaxy evolution. Most models assume galaxies grow through mergers or gradual accretion, becoming increasingly messy over time. Yet here's a galaxy that appears meticulously curated, its structure preserved against the chaos of the cosmos. Even more intriguing, follow-up observations revealed a second, fainter ring of stars beyond the first, a detail that hints at multiple epochs of star formation, as if the galaxy pulsed with activity in rhythmic bursts. Perhaps the most unsettling discovery is that Hoag's Object isn't entirely alone. A handful of similar Hoag-type galaxies have since been found, each with their own quirks but sharing that eerie, detached ring structure. Their existence suggests there might be an entire subclass of galaxies operating by rules we don't yet grasp. For now, Hoag's Object remains a cosmic masterpiece we can't quite explain, a reminder that even in a universe governed by physics, there's still room for the inexplicably perfect. Black holes have long been cosmic paradoxes, regions where the rules of physics seem to break down, leaving even the most brilliant minds grappling with contradictions. One of the most enduring puzzles is the black hole information paradox, a collision between two foundational theories, quantum mechanics and general relativity. According to Einstein's equations, anything that crosses a black hole's event horizon is gone forever, crushed into the singularity. But quantum mechanics insists that information, the fundamental details of particles and their states, can never truly be destroyed. So what happens when a black hole swallows a star, a planet, or even just a single atom? Is that information lost, or is the universe somehow keeping receipts? The paradox sharpened in the 1970s when Stephen Hawking made a startling discovery. Black holes aren't entirely black. They emit radiation now called Hawking radiation, due to quantum fluctuations near the event horizon. Over eons, this radiation causes black holes to evaporate, vanishing completely. But here's the catch: Hawking radiation appears random, carrying no trace of the information swallowed by the black hole. If the hole disappears, where does the information go? This contradiction threatens the bedrock of quantum theory, which demands that information be preserved even if scrambled beyond recognition. Imagine burning a book and insisting the ashes still contain every word. Only in this case, the ashes are featureless thermal radiation. For decades, physicists split into camps. Some, like Hawking himself, argued that information really is obliterated, a heresy that would force a rewrite of quantum laws. Others, like Leonard Susskind, championed the holographic principle, a radical idea that information isn't lost but encoded on the black hole's surface like a cosmic DVD. According to this view, the event horizon acts as a pixelated screen, storing data about everything that falls in, while the third dimension we perceive is an illusion. The math suggests that a black hole's entropy, its information content, is proportional to its surface area, not its volume, hinting that the universe might fundamentally be a two-dimensional information structure in disguise. Breakthroughs in recent years have tilted the scales toward information preservation. In 2016, physicists calculated that Hawking radiation might not be random after all. Subtle quantum entanglement between particles inside and outside the black hole could teleport information back out like a cosmic game of telephone. Then came the revelation of islands in the black hole's interior, regions where information could hide before eventually leaking back into the universe. These ideas, while mathematically elegant, stretch our intuition to the limit. They suggest that black holes might be more like puzzles than prisons, their secrets slowly unraveling as they evaporate. Yet mysteries remain. If information escapes, how does it avoid violating relativity's stricture that nothing can exit a black hole? Some theories invoke wormholes or higher dimensions, while others propose that spacetime itself is more fluid than we thought, with black holes serving as portals to deeper layers of reality. The paradox has even spurred experiments with analog black holes in labs, using sound waves or light to mimic event horizons and study how information might behave. What makes the information paradox so profound is what it reveals about our quest to unify physics. Black holes are the ultimate testing ground, places where gravity and quantum mechanics must finally reconcile. Whether the solution lies in holograms, firewalls, or something stranger, one thing's certain: the universe refuses to let information disappear without a trace. The paradox isn't just about black holes, it's a clue that reality might be far weirder and far more interconnected than we've dared to imagine. At the edge of our solar system, something massive is tugging at the fabric of space, and we can't see it. This is the mystery of Planet 9, a hypothetical world up to 10 times the mass of Earth, lurking somewhere beyond Neptune. The evidence for its existence isn't a direct observation but a series of cosmic breadcrumbs, clusters of Kuiper belt objects whose orbits tilt and cluster in ways that defy the gravity of the known planets. It's as if an unseen hand is herding these icy bodies, guiding them along paths that converge in a way that statistics say shouldn't happen by chance alone. The hunt for Planet 9 began in earnest in 2014, when astronomers Chad Trujillo and Scott Shepard noticed oddities in the orbits of distant objects like Sedna, a dwarf planet that loops far beyond Pluto on a stretched, lonely path. But the case solidified in 2016 when Caltech's Konstantin Batygin and Mike Brown modeled these quirks and found that a single, distant planet could explain them all. Their simulations suggested a world 20 times farther from the Sun than Neptune, tracing a slow, elliptical orbit that takes 10 to 20,000 years to complete. Yet finding it is like searching for a needle in a cosmic haystack. Unlike stars, planets don't emit their own light, they only reflect sunlight, and at such distances that reflection would be vanishingly faint. Telescopes like Subaru on Mauna Kea have scanned vast swaths of sky, sifting through billions of dim points of light for the telltale motion of a slow-moving world. Every so often, a candidate emerges, like the 2019 detection of a potential object in data from the Dark Energy Survey, only to fade into statistical noise under closer scrutiny. The intrigue deepens with alternative explanations. Could the gravitational anomalies stem not from a planet but from something even stranger, like a primordial black hole? These hypothetical relics from the Big Bang, no larger than a grapefruit but as massive as a planet, would exert the same gravitational pull while emitting no light at all. The idea gained traction in 2020 when physicists proposed that Planet Nine's effects could match a black hole's, sparking proposals to hunt for telltale flashes of gamma rays as dark matter annihilates in its vicinity. For now, Planet 9 remains a shadow, a tantalizing what if that challenges our understanding of the solar system's edges. Whether it's a rogue planet captured by the sun's gravity, a black hole fossil, or a statistical mirage, its absence is as provocative as its potential existence. Every unanswered question pushes us to look deeper, reminding us that even in our cosmic backyard, there are still worlds left to discover, hidden in the dark. Nebulas are nature's most breathtaking masterpieces, vast clouds of dust and gas sculpted by stellar winds into ethereal swirls and tendrils that glow with otherworldly colors. But sometimes the cosmos throws us a curveball, crafting something so uncannily precise it looks man-made. Enter the Red Rectangle Nebula, a cosmic anomaly surrounding the star HD 44179 in the constellation Monoceros. This isn't your typical wispy nebula. Instead, it's a near-perfect geometric structure, its stark X-shaped beams and layered rectangular planes defying every expectation of how these celestial clouds should behave. The first thing that strikes you about the red rectangle is its symmetry. Most nebulas are chaotic, shaped by explosive stellar deaths or turbulent magnetic fields. But here, the dust and gas align with an almost architectural precision, forming nested rectangles that glow a deep, eerie red. Astronomers believe the central star, a dying binary system, is responsible for this bizarre geometry. As one star sheds its outer layers, its companion star's gravity funnels that material into opposing cones, creating the X-shaped structure we see. The rectangle illusion comes from our vantage point viewed edge-on. The cone's walls appear as straight lines, like looking down the length of a flashlight beam. But the weirdness doesn't stop there. The nebula's chemistry is just as puzzling as its shape. Spectroscopic studies reveal an abundance of complex organic molecules called polycyclic aromatic hydrocarbons, or PAR carbon-rich compounds more commonly found in soot or engine exhaust. These molecules fluoresce under ultraviolet light, giving the nebula its crimson hue. Even stranger, the red rectangle emits a mysterious set of spectral lines known as the unidentified infrared bands, features seen in other cosmic environments but never fully explained. Some scientists speculate these could be signatures of exotic carbon-based structures, perhaps even precursors to life's building blocks. Theories about how this structure formed read like a cosmic detective novel. One leading idea involves a dense disk of dust around the binary star, so thick it redirects the outflows into bipolar jets. Over time, these jets could have carved the nebula's sharp edges like water sculpting canyon walls. Another possibility is that magnetic fields, twisted by the star's orbital dance, channeled the material into these precise formations. Yet no simulation perfectly replicates the red rectangle's stark geometry, leaving gaps in our understanding. What makes this nebula truly special is its rarity. Out of the thousands of planetary nebulas catalogued, none match its angular perfection. It's a reminder that even in the vastness of space where chaos reigns, nature occasionally drafts with a ruler, creating structures so precise they challenge our assumptions about the universe's artistry. Whether it's the result of unseen physics, cosmic coincidences, or something even stranger, the red rectangle stands as a testament to the fact that the universe still holds wonders we can't yet explain. Stars aren't supposed to come back from the dead, yet the universe loves breaking its own rules. Take white dwarfs, the dense, Earth-sized cores left behind when sun-like stars exhaust their nuclear fuel. These stellar embers slowly cool over billions of years, fading into darkness, until something reignites them with a cosmic jolt of energy. Enter the zombie stars, white dwarfs that somehow cheat death, flaring back to life in violent, unpredictable ways that defy every textbook model of stellar evolution. The most infamous case is Tycho's supernova, a star that exploded in 1572 with such brilliance it was visible to the naked eye for over a year. For centuries, astronomers assumed it was a classic type Ia supernova, the thermonuclear detonation of a white dwarf pushed past its mass limit by siphoning gas from a companion star. But in 2015, the Chandra X-ray Observatory spotted something chilling near the blast's epicenter, a surviving white dwarf bruised but intact. How could this be? Type Ia supernova were thought to be total annihilation events, leaving no remnant behind. This star didn't just survive its own funeral, it walked away from a blast powerful enough to outshine entire galaxies. Then there's LP 40-65, a white dwarf caught in the act of resurrection. Discovered in 2018, this rogue star streaks through the Milky Way at nearly 2 million miles per hour, trailing a shockwave of ionized gas. Spectroscopic analysis revealed it was once part of a binary system that underwent a partial supernova, a failed explosion that ejected enough material to send the white dwarf careening through space like a cosmic cannonball, but left it intact. The implications are staggering. If some white dwarfs can survive supernova, even partially, our entire understanding of these standard cosmic candles used to measure the universe's expansion might need revision. The real jaw-dropper came with SDSS J124 plus 0710, a white dwarf spotted pulsing with inexplicable bursts of energy. Dubbed the Phoenix Star, this object should have been cold and inert. Instead, it periodically reignites its nuclear furnace, fusing leftover helium in spasms of heat that mimic a newborn star. The likely culprit, a rogue planet or brown dwarf that strayed too close, its gravitational shredding dumping fresh fuel onto the white dwarf's surface like gasoline on dying embers. These stellar cannibalism events create Frankenstein stars, undead hybrids that blur the line between dead and alive. What makes zombie stars so revolutionary isn't just their defiance of expectations, it's what they reveal about the extreme physics at play in white dwarfs. Their survival hints at asymmetrical supernova, where explosions might kick the white dwarf away like a rocket detaching from its payload. Their resurrections suggest that even dead stars can hoard secret caches of fuel, waiting for the right trigger to burn again. And their very existence challenges our cosmic accounting. If white dwarfs can fake their deaths or die incompletely, how many other stellar ghosts are lurking in the data, masquerading as something they're not? Perhaps the most unsettling thought is that our own sun one day might join the undead. 5 billion years from now, after swelling into a red giant and shedding its outer layers, it'll collapse into a white dwarf quietly at first. But if a passing star or planet disturbs its slumber, who's to say it won't flare back to life in one last defiant blaze? the universe, it seems, has a flair for the dramatic, rewriting the endings of even the most well-understood stellar stories. Today's moon is a quiet, geologically dead world. No volcanoes, no shifting tectonic plates, and certainly no global magnetic field to shield it from the solar wind. But drill into its ancient rocks and you'll find a startling secret. This barren orb was once alive with magnetic activity. Samples brought back by the Apollo missions contain minerals magnetized in ways that only make sense if the moon once had a magnetic field as strong as Earth's, despite being just a quarter of our planet's size. The question isn't just how a body so small generated such a field, but why it vanished without a trace. The answers could rewrite what we know about planetary magnetism, and even hint at a lunar past far more dynamic than its cratered face suggests. The leading theory points to a molten core in motion. Earth's magnetic field comes from what's called a dynamo, a churning ocean of liquid iron in its outer core, spinning like a cosmic generator as the planet rotates. For the moon to have had a similar field, it too would have needed a molten core, circulating with enough energy to sustain magnetism. But here's the puzzle: the moon is too small to hold onto that kind of heat for long. Unlike Earth, its core should have cooled and solidified billions of years ago. Yet the magnetic traces in Apollo rocks suggest the field lasted for over 1 billion years, vanishing only around 1 billion years ago. Something kept the moon's core simmering long after physics said it should have gone cold. One tantalizing possibility involves colossal impacts. The moon's early history was marked by violent collisions, like the one that carved the South Pole Aitken Basin, a crater so vast it reaches deep into the lunar mantle. These impacts might have stirred the moon's core like a spoon in a cup of coffee, injecting enough turbulence to kickstart a temporary dynamo. Simulations show that a moonquake of that scale could have disrupted the core's layers, creating currents that generated magnetism. But this raises another mystery. If impacts powered the field, why did it persist for eons after the bombardment period ended? That's where tidal forces come in. Early in its history, the moon orbited much closer to Earth, and our planet's gravity would have stretched and flexed its interior like warm taffy. This constant kneading, known as tidal heating, could have kept the core molten long after natural cooling should have shut it down. Think of it as planetary friction, the same process that drives the volcanic eruptions on Jupiter's moon Io. But as the moon gradually drifted outward, Earth's grip weakened and the dynamo sputtered out, leaving behind only fossilized magnetism locked in ancient rocks. There's a wild card in this story, the possibility of a runaway dynamo fueled by crystallization. As the moon's core cooled, iron might have begun solidifying at the boundary with the mantle, releasing buoyant, lighter elements as it did so. This process, akin to salt rising to the surface of evaporating seawater, could have created convective currents strong enough to sustain magnetism even in a shrinking core. It's a delicate balance: too much crystallization and the core freezes entirely, too little and the dynamo never ignites. The moon's field might have been the Goldilocks result of this precarious phase, flourishing briefly before fading into silence. What makes the moon's lost magnetism so fascinating isn't just the how, but the why now. The timing of its disappearance coincides with a period when the moon's surface was still geologically active, with lava flows erasing older craters. Did the dying dynamo trigger these eruptions, or was it the other way around? And could similar processes explain why some exoplanets' worlds far smaller than Earth show hints of magnetic activity? Every rock brought back from the moon carries a fragment of this puzzle, whispering secrets about how even the quietest worlds can have turbulent pasts. The moon's magnetic field may be gone, but its legacy lingers, challenging us to rethink what's possible in the cosmos, one tiny, magnetized grain at a time. Saturn's North Pole hides one of the solar system's most hypnotic mysteries, a colossal, six-sided storm so precise it looks engineered by aliens. Known as Saturn's hexagon, This swirling vortex spans nearly 20,000 miles across, large enough to engulf 4 Earths side by side, with winds screaming at over 300 miles per hour. Unlike the chaotic cyclones of Jupiter or the fleeting storms of Earth, this geometric behemoth has persisted for at least 4 decades, possibly much longer, its razor-sharp edges defying every expectation of how planetary weather should behave. The hexagon's discovery in the 1980s by NASA, a Voyager missions left scientists stunned. Atmospheric patterns tend toward curves or spirals, not polygons. Yet Cassini's later close-ups confirmed it wasn't an illusion. This was a stable, rotating hexagon, a cosmic honeycomb etched into Saturn's atmosphere. The secret might lie in the physics of spinning fluids. Lab experiments with water in rotating tanks show that under certain conditions, turbulence can self-organize into polygonal shapes. Saturn's rapid rotation, a day there lasts just 10.5 hours combined with its deep atmosphere of hydrogen and helium, could forge this natural geometry like a cosmic lathe carving the storm into shape. But why a hexagon? The shape may emerge from standing waves, where competing wind currents create stable nodes of high and low pressure, much like vibrations in a guitar string produce harmonics. On Saturn, these waves might stretch and fold the jet stream into a 6-sided pattern, locking it in place like a celestial fingerprint. Some models suggest the hexagon's stability comes from its depth, a structure rooted far below the visible cloud tops, where denser layers of gas act like an anchor, preventing the storm from dissolving into chaos. The most baffling trait isn't just its shape, but its endurance. Earth's hurricanes dissipate in days. Jupiter's great red spot, while centuries old, is slowly shrinking. Yet Saturn's hexagon has outlasted generations of scientists, its structure virtually unchanged since we first glimpsed it. One theory points to Saturn's lack of solid topography. Without mountains or oceans to disrupt airflow, the storm could theoretically spin indefinitely, a perfect engine fed by the planet's internal heat and rotation. There's another layer to the puzzle, the hexagon's eerie synchronization with Saturn's seasons. As the planet's north pole tilted toward the Sun during its 30-year orbit, Cassini observed the hexagon darkening, its clouds reacting to sunlight in ways we still don't fully understand. This hints that the storm isn't just a superficial pattern but a window into Saturn's deeper atmospheric machinery, where hidden currents and temperature gradients choreograph its motion. What makes the hexagon so mesmerizing is how it bridges order and chaos, a mathematical shape born from turbulence, a fleeting storm frozen in time. It's a reminder that nature's rulebook is far stranger than we imagine, capable of crafting precision from pandemonium. Whether it's a quirk of fluid dynamics, a resonance phenomenon, or something beyond our current physics, Saturn's hexagon stands as one of the solar system's most dazzling enigmas, a 6-sided sentinel guarding secrets we've only begun to unravel. Some galaxies blaze with the light of 1 trillion stars, their spirals and clusters impossible to miss. Then there are the cosmic phantoms, ultra-diffuse galaxies, or edges so faint they blur into the darkness around them. Picture a galaxy as large as the Milky Way, but with only 1% of its stars, scattered so thinly that telescopes almost glance right past them. These aren't just dim, they're nearly invisible, ghosts woven into the fabric of the cosmos. Yet beneath their wispy exteriors lies a paradox. Some, like Dragonfly 44, weigh as much as our own galaxy, their mass hidden in vast cocoons of dark matter. How can something so faint be so heavy, and what does their existence say about the rules or loopholes of galaxy formation? The story begins with Dragonfly 44's discovery in 2016, a smudge of light in the Coma cluster that shouldn't have been there. Most galaxies in dense clusters are either bright ellipticals or shredded remnants, not fragile, sprawling UDGs. Yet here was Dragonfly, its stars so sparse you could peer straight through it like gauze stretched across the night. Measurements of its velocity dispersion, how fast its stars move, revealed the shock. Despite having almost no visible matter, its stars were orbiting so quickly that an immense gravitational force must be holding them together. The math pointed to a dark matter halo rivaling the Milky Way's, an unseen anchor keeping this wisp from dissolving into the void. This raises a thorny question. How does a galaxy end up with 99.9% of its mass in dark matter? One theory suggests UDGs are failed galaxies, systems that started forming stars early on but had their gas stripped away by cluster tides or supernova winds, leaving only a skeletal framework of dark matter and a handful of surviving stars. Others propose they are fluffed up by violent interactions, their stars scattered like dandelion seeds during close encounters with larger galaxies. There's even a wilder idea that UDGs are the bloated remnants of ancient, ultra-compact galaxies, stretched beyond recognition by cosmic expansion or dark energy's push. But Dragonfly isn't alone in defying expectations. In 2019, astronomers found another UDG nicknamed the Ghost of Mirach, which appeared to lack dark matter entirely, a direct contradiction to Dragonfly's profile. This flip side of the coin hints that UDGs might not be a single category but a spectrum of misfits, each telling a different story about how galaxies live and die. Some could be dark matter fortresses, others galactic shadows cast by unseen forces. The implications ripple outward. If UDGs are more common than we thought, thousands likely lurk undetected in clusters. They might solve the missing satellites problem, where simulations predict more small galaxies around the Milky Way than we observe. Perhaps we've been missing them all along, their faintness hiding them in plain sight. Even more tantalizing, their dark matter dominance could make them ideal labs for studying this elusive substance, its gravity sculpting these galaxies into cosmic smoke rings we can finally map. What makes ultra-diffuse galaxies so mesmerizing isn't just their mystery, it's how they stretch our definitions. They force us to ask, what is a galaxy if not a beacon of light? Is it the mass, the structure, or some interplay we've yet to grasp? In the quietest corners of the universe, these ghosts whisper that darkness might be just as important as the stars, and that sometimes the faintest glimmers hold the heaviest secrets. Most planets we know orbit stars, basking in their warmth like children huddled around a campfire. But venture into the void between star systems, and you'll find a far stranger breed of world rogue planets drifting alone through the eternal night. These cosmic nomads, untethered from any sun, wander the galaxy in perpetual darkness, their surfaces frozen to temperatures near absolute zero. Yet what's truly mind-bending isn't just their existence, but their sheer abundance. Astronomers estimate there could be billions, perhaps even trillions, of rogue planets in the Milky Way, outnumbering stars by as much as 20 to 1. So how does a planet end up alone? Some are born that way, failed stars or brown dwarfs, too small to ignite nuclear fusion, condensing directly from collapsing gas clouds like starlight that never quite flickered to life. Others are exiles, violently ejected from their home systems during gravitational tugs of war with sibling planets or passing stars. Imagine a young solar system in chaos, worlds jostling for position, until one gets flung outward like a marble launched from a slingshot, doomed to drift forever. Simulations suggest this might happen more often than we think, especially in densely packed star-forming regions where celestial close encounters are common. Detecting these lone wanderers is like searching for black ink on black paper. Without a host star's light to illuminate them, rogue planets are nearly invisible but not entirely. Two methods have given us glimpses. Microlensing occurs when a rogue planet's gravity bends and magnifies the light of a distant star behind it, creating a fleeting bright spot in telescope data. It's a cosmic loophole using gravity itself to reveal the unseen. The second method relies on heat. Young rogue planets, still glowing from the energy of their formation, emit faint infrared signatures. In 2020, astronomers using the Very Large Telescope in Chile spotted one such object, a Jupiter-sized rogue just 80 light-years away, its dim glow betraying its presence. The most tantalizing rogue planets might be those with hidden oceans. While surface temperatures are brutal, tidal heating or radioactive decay could maintain liquid water beneath thick ice shells, much like Jupiter's moon Europa. A rogue planet with a subsurface ocean could, in theory, harbor life, sustained by geothermal vents or chemical reactions in the dark. The idea reshapes our definition of habitable. Life might not need a star. It could thrive in the eternal night between the stars, huddled around planetary heat like a cosmic fireplace. Their prevalence raises profound questions. If rogue planets dominate the galactic population, could they be ferrying life between star systems, acting as frozen arcs over billions of years? Some theories even suggest they could be the missing repositories of dark matter, though evidence remains thin. What's certain is that these lonely worlds challenge our planet-centric view of the universe. We think of planets as companions to stars, but the cosmos might see them differently, as free agents, untethered and wild, carrying their secrets through the interstellar dark. Every rogue planet we find is a reminder the universe is far stranger and far more untamed than we've dared to dream. In the vast, silent archives of the cosmos, some discoveries feel less like scientific observations and more like stumbling upon an ancient, indecipherable codex. That's precisely the aura surrounding Hani's Voorwerp, a celestial oddity so bizarre it's been dubbed the Voynich manuscript of space. First spotted in 2007 by Dutch schoolteacher Hanny van Arkel, a volunteer in the Galaxy Zoo Citizen Science Project, this enigmatic green blob floats near the spiral galaxy IC247, glowing with an eerie, ghostly light. What makes it so confounding isn't just its appearance, but the fact that it shouldn't exist. A massive cloud of ionized gas, lit up like a neon sign in the void with no obvious power source. The key to the mystery lies in its color. The Voorwerp's vivid green hue comes from highly ionized oxygen, a telltale signature of gas blasted by intense ultraviolet radiation. Normally, that radiation would come from newborn stars or an active galactic nucleus, but here's the twist. The Voorwerp isn't forming stars, and the nearest galaxy, IC247, shows no signs of hosting a black hole energetic enough to illuminate it. That's when astronomers uncovered the cosmic time delay at play. The Voorwerp isn't being lit by the galaxy as it is today. It's a light echo, a fossil imprint of a cataclysmic event that occurred tens of thousands of years ago. The galaxy's core once roared with quasar-like fury, its supermassive black hole gorging on matter and belching out radiation so powerful it lit up the Voorwerp like an interstellar bonfire. Then, abruptly, the engine switched off, leaving the Voorwerp as the last glowing ember of that forgotten inferno. But the plot thickens. The Voorwerp isn't just a passive billboard, it's structurally unique. Most gas clouds in the universe are chaotic, their edges blurred by stellar winds or gravity. The Voorwerp, by contrast, has razor-sharp boundaries, as if someone sliced it out of the cosmos with a knife. Then there's the hole punched through its center, a void where the gas is mysteriously absent, as though something blew a tunnel straight through it. Some theorists suggest this could be the wake of a jet from IC247's black hole, a particle beam so intense it cleared a path like a cosmic sandblaster. Others wonder if the Voorwerp is a tidal tail, a streamer of gas ripped from a passing dwarf galaxy and left hanging in space, frozen in the act of dissipation. The most tantalizing clue: the Voorwerp isn't alone. Since its discovery, astronomers have identified a handful of similar Voorwerps, Dutch for little Voorwerps, scattered like glowing graffiti across the universe. These objects suggest that quasars don't fade gently. They shut off abruptly like a cosmic circuit breaker, leaving behind ghostly afterimages that linger for millennia. They're time capsules offering snapshots of galactic violence on a scale we're only beginning to fathom. What makes Hani's Vorwerp so mesmerizing isn't just its otherworldly glow, it's the way it forces us to rethink the life cycles of galaxies. We tend to imagine cosmic processes as slow and stately, unfolding over billions of years. But the Vorwerp tells a different story, one of sudden endings, of light that outlives its source, of the universe's capacity to leave behind cryptic clues in the most unexpected places. It's a reminder that space isn't just a collection of stars and planets, it's a palimpsest, layered with echoes and remnants, waiting for patient observers to piece together its hidden narratives. Just when we thought Tabby's star was the universe's ultimate flickering enigma, along came Epic 204278916, a young, sun-like star in the Scorpius constellation that doesn't just dim, but plummets in brightness by up to 65%. That's not a typo. For comparison, Tabby's star's deepest dips cap around 22%, already enough to spark debates about alien megastructures. But Epic 204278916 doesn't just flirt with cosmic mystery. It dives headfirst into the unknown, extinguishing 2/3 of its light in irregular, dramatic drops that leave astronomers scrambling for explanations. What makes this star so perplexing isn't just the scale of its dimming, but the sheer chaos of its light curve. Unlike the predictable shadows cast by orbiting planets, Epic drops are erratic, some lasting days, others mere hours, with no discernible pattern. Observations from the Kepler Space Telescope's K2 mission revealed one particularly jaw-dropping event where the star's light faded by 65% over 25 days. Then abruptly rebounded as if nothing had happened. It's as if something colossal, something utterly unlike anything in our solar system, is drifting in front of it, blocking its light in fits and starts. Theories abound, each with its own tantalizing twist. The leading contender, a monstrous, warped disk of dust and debris, possibly the aftermath of a planetary collision or a young star's chaotic birth throes. Epic is estimated to be just 5 million years old, a cosmic toddler, and young stars often sport protoplanetary disks. But here's the catch: even among its peers, Epic behavior is extreme. Most circumstellar disks thin out smoothly, casting gentle shadows. This one would need jagged, uneven clumps, some dense enough to blot out 65% of the star's light, others translucent enough to vanish without a trace. Then there's the wild card, magnetic activity. Young stars are notoriously volatile, with magnetic fields so powerful they can starve entire hemispheres of light through sunspots or plasma loops. Could Epic dimming be the result of hyperactive star spots, far larger and weirder than anything in our solar neighborhood? It's possible, but the math is shaky. Even the most aggressive starspot models struggle to account for such extreme, asymmetric dimming without invoking impossibly large or dark surface features. And of course, there's the elephant in the room. Could this be another candidate for alien engineering? While it's the least likely explanation, Epic's sheer audacity invites speculation. If a civilization were building a Dyson swarm, a constellation of energy-harvesting satellites around a young star, might their construction phases create similar erratic shadows? The idea is a stretch, but it underscores how thoroughly this star defies convention. What truly sets Epic apart is its context. Unlike Tabby's star, which is middle-aged and solitary, Epic is a child of the cosmos, still swaddled in the leftovers of its formation. That youth might hold the key. Perhaps we're witnessing the violent adolescence of a planetary system, where moons shatter, planets migrate, and rings of debris twist into bizarre, light-eating shapes. Or maybe Epic is teaching us that stars, like humans, go through phases of rebellion, throwing tantrums of dust and magnetism we've yet to fully comprehend. For now, Epic 204278916 remains a puzzle wrapped in a mystery. Its flickers a siren song to astronomers. Every new observation peels back another layer, but the core question lingers. In a universe full of shadows, what's casting this one? The answer, whatever it is, promises to stretch our understanding of how stars and their planetary families grow or collapse in the dark. From the wow signal's tantalizing whisper to the Great Attractor's invisible pull, from rogue planets wandering the cosmic dark to zombie stars that refuse to die, we've journeyed through 25 of the universe's most jaw-dropping anomalies. Each one is a reminder that the cosmos operates on a scale beyond human intuition, where the familiar laws of physics twist into strange new shapes. These aren't just gaps in our understanding, they're neon arrows pointing to uncharted territories, screaming that there's so much more to discover. Think about it, we live in an era where we can map the afterglow of the Big Bang, yet we still can't explain what 95% of the universe is made of. We've photographed black holes, but we don't know if information survives their grasp. We've found planets orbiting stellar corpses, galaxies made mostly of dark matter, and storms shaped like hexagons, each discovery peeling back a layer only to reveal another mystery beneath. The more we learn, the clearer it becomes. The universe isn't just stranger than we imagine, it's stranger than we can imagine. This is why we keep looking up. Not just for answers, but for the thrill of the questions themselves. Every unexplained signal, every cosmic oddity, is an invitation to stay curious, to challenge assumptions, and to embrace the humility of not knowing. Maybe you're fascinated by the Fermi Paradox's chilling silence or the red rectangle's unnatural geometry. Maybe you lose sleep over the thought of dark energy ripping the universe apart. Whatever sparks your wonder, remember you're part of a story that's still being written, one observation, one theory, one what if at a time. So here's to the anomalies, the outliers, the cosmic rule breakers that keep science honest and imagination alive. If you loved this dive into the unknown, make sure to subscribe and hit that notification bell. We've got plenty more mysteries to unravel together. And drop a comment below. Which of these 25 enigmas blew your mind the most? Is there another cosmic head-scratcher you think deserves the spotlight? The universe is vast, unpredictable, and endlessly fascinating, and the next great discovery might just be a click, a question, or a telescope flicker away. Keep wondering, keep exploring, and above all, stay amazed. The cosmos isn't done surprising us.